Thanks to all the organizers for inviting me. Thanks for all of you for hanging around till the last talk, and it's really inspiring to see so many people interested in this topic that I have been interested in for many years now. So I'm going to talk about this new tool called isolating cuts, but let's start off by some very basic definitions. I guess most of you already know this, but let's make sure we are on the same page. Okay, so I'm going to be talking about cuts. Cuts are bipartitions of vertices. Equivalently, they are the edges that go from one side to the other, and a recurring theme would be talking about minimum cuts. These would normally, if it's an unconstrained minimum cut, it's simply the cut with the smallest value. Value could be the sum of weights of the edges if the edges have weights, or the cardinality of the edges if the edges don't have weights. And in some cases, we'll put restrictions on the set of cuts we are considering when taking the minimum. Those restrictions, as they come up, we'll talk about them. We'll focus in this talk pretty much exclusively on graphs that are undirected, but we'll allow edges to have weights. Weights need to be positive, and they can, I would assume for most of the talk, that the weights are polynomially bounded in the size of the graph. This is not a critical assumption. It can be removed at the cost of certain extra terms in running times, but for the sake of this talk, I'll make that assumption. I'm going to be allowing parallel edges. So the graphs on the right, on the left, the two graphs on the left, those are graphs that I will be talking about. The graph on the right, I won't be talking about except on the very last slide. Okay, so that's what I'm going to be talking about. Now, the two basic definitions that I'm going to use throughout the talk is that of a global min cut. This is simply, as I said, the unconstrained minimum value cut of the graph. It may not be unique. There could be several of these. We are also going to be talking about an ST min cut, which is one of these cases where I will restrict the set of cuts before I take the minimum. An ST min cut, where S and T are two vertices, is simply the minimum cut such that S and T are on different sides of the cut. Okay? So those are two basic things that most of us are familiar with. I have an example there. I'm not going to go over it in detail. Most of you already know what these things are. All right, so let me start off with a very basic, simple question. The question is the following. Suppose I gave you a maximum flow algorithm, or even a maximum flow in a graph. How would you find an ST min cut? So again, I have a maximum flow given to you from S to T. I just want you to report an ST min cut of the graph. Anyone has a quick answer?
You consider the residual graph and do BF
Okay, so let's look at his answer. So what he's saying is that, well, let's take the graph. Here I have drawn an example graph, and I have computed an ST max flow. So in this particular example, all the edges are unweighted, so edges have weight 1, and my flow also has value 1. So this is a max flow of the graph. Sorry, this is not a max flow of the graph. Let me draw a max flow of the graph. Okay, so this is a max flow of the graph. So now once I have a max flow, what I can do is I can compute the residual network. In this case, the residual network will look like this. It's kind of the opposite of the flow. And now in this residual network, I can just figure out what are the vertices that are connected, that are reachable from S. Okay, or what are the vertices that can reach T. These are, either of these two will define an ST min cut. Okay, in this case, for example, this degree cut of S is an ST min cut. Okay, good. So that's a very simple way of figuring out what an ST min cut is. And in fact, that just takes linear time. I'm just running some kind of BFS or DFS, some search procedure on top of my max flow. Okay, next question. Now that I know how to find an ST min cut, how can I use that to find a global min cut of the graph? So I gave you an algorithm that can find an ST min cut. What's the simplest way of using this gadget to compute a global min cut? Yes?
Run it for all players.
Run it over all pairs of vertices. Perfect. So I can take, I know that some pair of vertices is separated by my global min cut. So I can take every pair of vertices, find ST min cuts, whichever is the smallest, that's my global min cut. That's correct. Can we optimize that slightly more? Yeah?
You can put one vertex on throughout as one side and run it over all the other vertices.
Perfect. So what he's suggesting is I don't really need to run it over all pairs of vertices. I can fix one vertex. Okay, so this vertex is going to be on one of the sides of the min cut, and then I iterate over all the other vertices. One of them must be separated from this fixed vertex by my global min cut. So I iterate over all these vertices, find ST min cuts, and report the smallest. So here's the algorithm. You simply fix a vertex, iterate over all the other vertices, find ST min cuts, report the smallest. That's the correct algorithm, takes n max flow calls or n minus 1 max flow calls. So the first question that we are going to spend about half an hour on is, can we do better? Given this gadget of an ST min cut, can we find a global min cut of a graph faster than iterating over n minus 1 different vertices and running n minus 1 max flows? Okay, so that's our question. All right. So again, this is the simple min cut algorithm that I just described. Now one thing to notice is, what are we really doing when we are iterating over all these vertices T? What we are really doing is we are searching for that one vertex that is separated from this fixed vertex S by the min cut. Okay? We just need one such vertex. So if someone came to you and said, look, I'll give you this ST min cut algorithm, I'll also give you this one vertex T that's separated from S in the global min cut. I'm telling you that. Then all you need to do is run just a single ST min cut at that point. Right? I just take that particular pair, S and T, run max flow, that's going to be my global min cut. So if somebody found me a good vertex, a vertex that's separated from S, then my task becomes a lot easier. So we can rephrase our question to ask, can we actually efficiently find a pair of vertices S and T that are on different sides of the global min cut? If you can find such a pair, then our problem reduces to ST min cuts and therefore to max flows. All right. Now let me make the following assumption for a minute. Let's say that my min cut, the global min cut, is actually balanced. By that, what I mean is that there are a constant fraction of vertices on both sides of this cut. Okay? So if I had that property, let's say think of it as half the vertices on the left, half the vertices on the right. If I had that property, is it easier to find a pair ST that's separated by the min cut? How would we go about this? Yeah?
Randomly sample.
Random sampling. Okay, so all I need to do is just sample two vertices, and I will have a constant chance that these two vertices would land on the two different sides. So here's a simple algorithm then. I sample two vertices, I find the ST min cut, okay? And I repeat this process log n times because I only have constant probability that I am getting the global min cut. After repeating this, I have pretty good confidence that I found one pair that's separated by the global min cut. So I take all the min cuts, ST min cuts I found, and I report the one that's smallest. And this algorithm will succeed with probability that's close to 1. Okay? So let's take this intuition and try to apply it in a more general situation. So what's the problem in a general situation? I might not have a balanced global min cut. Okay, my global min cut might have a small number of vertices on one side and a large number of vertices on the other side. If that's the case, I am in more trouble because now I really need to find some vertex on that small side, and just blindly random sampling might not be so great. Okay? So let me try something. Let's say that the smaller side of the min cut has k vertices. Okay? In general, I don't know what the value of k is, but for now, just bear with me, assume that k is known. Okay? So suppose k were known, if all I really wanted is to find a sample that gets a vertex on the smaller side, I would have to sample vertices at a rate that's about 1 over k. Right? If I do that, then I expect to see one vertex on the smaller side. and if I do this a bunch of times, then one of those samples would have exactly one vertex on the smaller side. So here's what I now propose to do. I sample vertices at probability 1 over k, and I'll repeat this whole process log n times. This sample now is not 2 vertices, it can have more vertices. But if I had that property, if it was a good sample, so it has exactly one vertex on the smaller side, then what do I really need to find? I need to find min cuts that isolate individual vertices in my sample from the rest of my sample. So my sample now has a bunch of vertices. I don't know which of these vertices is on the smaller side of the min cut, but there's exactly one. So if I can find cuts that isolate individual vertices of my sample from the rest of the vertices, then the smallest among these is going to be my global min cut. Okay? So that's the algorithm that I described here. So take this example. Here my sample, let's say, has 3 vertices, V, C, and D. It so happens that D is the isolated vertex on one side of the min cut. So if I found the minimum cut that isolates D from B and C, that's going to be my global min cut. Now of course I don't know the identity of D. For all I knew, B or C might have been this isolated vertex. So I need to find cuts that isolate each of these vertices in my sample. Okay? So the problem that we really need to solve then is the following. I gave you a graph. I gave you this bunch of sampled vertices. I want you to find cuts that isolate one vertex from the rest of the sample vertices. So among all these cuts, I want to find the one that's minimum. This is what we call minimum isolating cuts. Any questions about the definition? Yes?
So you're just, in the end, are you only returning one cut? Like you're looking for each terminal, you find the minimum cut isolating that terminal, and then you only have to return the minimum of those? You don't have to return the rest?
So the way I will phrase the minimum isolating cuts problem, I need to return all of them. But for the application to minimum cuts, I just need the one that's smallest. I don't need all of them. Other questions? Yes?
So I'm a little confused. When you say you want to find a min cut that isolates a single vertex for HD, does that mean that from the 2 vertices that are in your sample size T, you want one of them to be the overall set of the cut?
So I couldn't hear all of it, but let me try to answer from what I heard and tell me if I didn't hear properly. So the sample set now is not of size 2. Sample set can be larger. Now look at any one vertex in that sample, any one terminal. Now look at all cuts that separate that terminal from the rest of the terminal. There are many such cuts in the graph. Among them, whichever is the smallest in value, that's the minimum isolating cut for that particular vertex, that particular terminal. Now what I want to do is I want to return the minimum isolating cut for all the terminals individually in your sample.
So there are k vertices in your sample, or?
So the number of vertices in my sample, for example, if I sampled at rate 1 over k, the expected number of vertices would be n over k. Yes?
Are you reusing information between these, or are you assuming it's like is your solution going to solve for if I only care about one vertex?
So at this point, I'm just defining a problem. And my problem is I have a graph and a subset of vertices. I want the smallest cuts that isolate individual vertices from the rest in the subset. Okay? Other questions? Yeah.
The solution here is pick one vertex here from the terminals, put all the other ones become a sink, and then do a steep max flow between them.
Exactly. That's the trivial. So what Safar is saying is that the trivial way to do this would be to iterate over all the vertices, and for each vertex collect all the other for each terminal collect all the other terminals into a single sink and run ST min cuts. That would be the trivial way of solving this. You're right. Any other questions? Okay, good. So that's my problem. So I've stated the problem earlier, so let me not restate it. But here in this example, as you can see, so there are 3 terminals. these are the sampled vertices B, C, and D, and I want cuts, minimum cuts that separate B from C and D, C from B and D, and D from B and C. Okay, and these are 3 such cuts that I have drawn. Now, once you see this question, the first thing you might think of is, how do these cuts interact? Instead of asking for a single cut, I'm asking for several cuts here, right? The number of cuts is the same as the number of terminals. So maybe these cuts overlap in weird ways. Right? Can I even represent these cuts in an efficient manner? So my first property, the first property that's interesting here, is that these cuts, at least one set of such minimum isolating cuts, are disjoint. Okay, so it was no coincidence on the previous slide that these red sets were all disjoint. Okay, that's something that's generally true. No matter what terminals I give you, there's always going to be a set of minimum isolating cuts that are disjoint. Okay, and therefore, as a corollary of that, I can represent all the minimum isolating cuts in linear space. Okay? So why is this true? Actually, the proof is extremely simple. So let's do the proof here. I'll also put it up there because I wasn't sure if I would get a board, but don't look there, look at the board. All right, so let's say 2 of the minimum isolating cuts overlap. Okay, so these are minimum isolating cuts for some terminal. So let's say the one on the left is for terminal T, and the one on the right is for terminal T prime. Now the first assertion is that in the intersection there are no terminals, because remember, these are sets that are isolating these terminals. So it contains exactly one terminal each, and those terminals must necessarily be in the different sets. So the intersection does not have any terminal. Okay? So now let's write our standard cut inequalities. So we can write the size of cut S plus the size of cut S prime. That's at least the size of the 2 different sets. And if you haven't seen this inequality earlier, this just follows from submodularity of cuts. It's not very hard to prove. It's actually very straightforward. So this just says that the 2 cuts represented by the original isolating cuts, together those cuts are at least as large as the 2 difference cuts. Okay? And at this point I'm done, because this implies that one of 2 properties is true. Either Fs is at least f of s minus s prime, or f of s prime is at least f of s prime minus s. Okay? At least one of these 2 must be true. And if one of them is true, so for example, if the first one is true, let's say this cut, the cut S, is at least as large as the cut S minus S prime, then S minus S prime is also a minimum isolating cut for T. Right? It's clearly an isolating cut for T, and it's smaller than what I started off calling the minimum isolating cut. Okay? So that means that I can uncross these 2 things. Even if they overlap, I can find a different isolating cut such that they don't cross anymore. And therefore, eventually, once I keep uncrossing, eventually I will end up with a set of cuts, a set of minimum isolating cuts that don't cross at all. Any questions about this proof? All right. Oh, sorry.
What exactly did you mean by submodularity in this context?
Oh, just that the cut function is a submodular function. Just the like this particular thing needs undirectedness, but it just follows from submodularity and the fact that the graph is undirected, so it's symmetric. Okay. Any other questions? Okay. All right. So we have established that these are subdisjoint objects that I'm trying to find. How do I still find them? Okay. So let me start off by describing an algorithm, and slowly we'll develop this algorithm. It's a very simple algorithm. So what I first do is I take my terminals. Again, terminals are these vertices that I'm trying to separate, and I do a binary encoding of the terminals. Okay, so I have 3 terminals here. I have encoded them as 1 0 0 1 1 1. Okay. Now I look at each bit position and I bipartition the terminals based on the value in that bit position. So for example, if I look at the first bit position, the one in blue, then the bipartition is C on one side, it has value 0, B and D on the other side, they have value 1. Similarly, if I look at the second bit position, the bipartition puts B on one side, it has value 0, C and D on the other side, they have value 1. So I create these bipartitions of the terminals. Let me call these bipartitions xk and yk, okay, for the kth bit position. Next, what I do is I find minimum cuts between the entire set xk and the entire set yk. So I contract the entire set xk into a single vertex, contract the entire set yk into a single vertex, and find the minimum st cut separating these 2 vertices in my graph. Okay, so that's my first algorithmic step. I do this binary encoding. Based on each bit position, I do a bipartition of the terminals, contract the terminals on the 2 sides of this bipartition, find an st min cut.
Sorry, do you find
Yes.
the cut itself or only the value of the min cut?
No, I find the cut itself.
Itself.
Yes.
You also need that.
Yes.
Okay, thanks.
All right, that's my first step. So let's see what happens after I do this. So for instance, in this graph, maybe I have found the red cut and the blue cut. Okay, these are my 2 minimum cuts for the 2 different bit positions. Now, if I take all the overlapping regions of these cuts, then I can define 2 raised to log t such overlapping regions. Okay? So again, I did a binary encoding. So how many bits did I have? Log t. Now for each bit position, I had a bipartition. Now these bipartitions overlap. So how many different overlapping regions will I get? 2 raised to log t. Okay? And that's going to be at most, let's say 2t, because I might have some rounding errors, but it's going to be order of t. So I look at all these different distinct regions. These are all disjoint. Okay, in this picture, I've shown them in yellow. So I've taken the red cut, the blue cut, and I've taken all the 4 regions that they define in my graph. Okay, let me call them S0, S1, S2, and S3. Questions so far? Yes?
Can you always enforce the isolating cuts in the form of partitions and vertices?
So I'm taking any set of cuts, and I'm just looking at all the vertices that are not separated by any of the cuts. They form each of my regions. Okay? Yes?
Can you explain how you encode the set T again?
Arbitrarily, just put a binary string on each of them.
You assign 0 and 1 for each.
Yes. Just label each, just number them 1 through t and write that out in binary. Other questions?
Yeah, so yeah, maybe I missed it. How is it log t as opposed to t? So you're not running for array.
So number all your terminals 1 through t, or let's say 0 through t minus 1. Write it out in binary. So that's log t bits.
That's true. Yeah.
Now for every bit, I have 1 such cut. So for every bit position, you look at everyone who got a 0 in that bit position, everyone who got a 1. These 2 groups contract into single vertices, find an st min cut.
Oh, I see. Yeah, that's perfect. Thanks.
Other questions? Okay. So I have these order t groups of vertices. I have split my set of vertices into these order t groups. Now, importantly, each group contains at most 1 terminal. right? Because every pair of terminals was separated by some bit position. So no two terminals can belong to the same region, same yellow group. There can be some groups that don't have any terminal, but every group can have at most one terminal. And this is the key property, the one in black in the middle, that every pair of terminals must be separated in the way that I have constructed these regions. My story about writing things out in binary and bipartitioning, that's just one way of doing it. You can do it in any way you want, but I want that every group, I create this partition of the vertex set such that every group contains at most one terminal, and I have only ordered T groups. Okay? The next phase of my algorithm is iterative. So now I'll take each of these yellow groups and do something with them. Yes, and I will iterate over all the groups. So let's see what we are going to do with this group S3. Okay, so what are we going to do with this group? Well, we take this group S3 and contract away everything else in the graph. So all the other groups get contracted into a single vertex. I call that Z3. Similarly, when I'm working with S1, I keep S1 alive, contract away everything else into a single vertex that I call Z1. Okay, and I iterate over all the groups. For each group, I do this. I contract away everything else into a single vertex. And then I run ST_min_cut subroutine again. This time between the terminal in the group I kept alive. So if I'm working on S3, then between the terminal T3 and this contracted vertex Z3 that contracted away everything else. So in this step, I'm actually running a lot of ST_min_cuts. Right? For each group, I'm running one ST_min_cut algorithm, where one terminal is the original terminal. That's part of the group I did not contract. And the other terminal is this fake vertex that I created by contracting away everything else. So once I found this ST_min_cut, so let's say that T3 Z3 min_cut, I simply return that as my minimum isolating cut for terminal T3. Yes?
So when you're contracting, you're like adding up all the edge weights going to like the weight of the edge from D to the supernode will be like the sum of all the.
Yeah, I mean just think of it as putting infinite edges between all the vertices I'm contracting, infinite capacity edges. So edges that go between the contracted set and the rest of the graph are unaffected. The contracted set just becomes a single vertex. Yeah. Okay? So that's my entire algorithm. So in the last step, whatever ST_min_cut returns, that's my minimum isolating cut. All right, so why does this work? I mean, I'm doing some funny thing at the end. Why doesn't that destroy my minimum isolating cut? Again, the proof is very simple. So the claim, of course, is that the Ti-Zi cut, so the Ti-Zi min cut is indeed the minimum isolating cut for terminal Ti. So why does it work? So again, let's, instead of looking at the board, let's go here. So why should it not work? Well, the reason it may not work is because in the process of contracting all these vertices into Z sub I, I might have destroyed my minimum cut, the isolating cut. Okay. If the minimum isolating cut stays alive, right? If the minimum isolating cut is a valid cut in the contracted graph, then of course I will return that cut. But if the minimum isolating cut was destroyed in the process, then I will return some garbage. So I need to argue somehow that it's not possible for me to destroy every minimum isolating cut by this contraction. Yes?
So even before that, like how do you make sure it's not in SI?
How do we make sure that?
Like so by the proof strategy you just said, so you're assuming that a minimum isolating cut cannot be inside SFI.
No, it can. If it is inside SI, that's good for me, because that cut is something I can identify in the last step. If it crosses into the other side that's getting contracted, that's bad for me, because that's a cut that hasn't survived my contraction.
I see. Oh, I see. Oh, yeah, it can.
Oh, but I just have a question. So, if you have a terminal set, in size of terminal set, many min cut operations, right, to find the ST min cut, you can find all the isolating cuts.
Yeah.
Here also you're repeating it like T times.
Okay, so we'll come to running times. So we'll talk about running time of this algorithm, but let's first establish that what we are getting is the right answer. Yes.
So just to clarify, you're trying to show that there is at least one minimum cut such that each of its edges is preserved.
That's right.
Okay. Is it easy to rule out all such cuts? Is it easy to see why like all such cuts might not survive?
Yeah, so there are easy examples where all of the minimum isolating cuts will not survive. But one for each terminal will survive. Yes. Okay. So let's look at why that happens. Why does the minimum isolating cut survive these contractions? So let's say it does not, in which case there must be some kind of a crossing that happens between my minimum isolating cut for some terminal T. So let's say this is my cut, and one of these xk, yk min cuts that I had obtained, right? Remember, what I contracted was everything that's outside the region defined by T. So one of these xk, yk min cuts must be overlapping my minimum isolating cut if I need to run into trouble. Now, if that happens, then let's first figure out where the terminals are. So this cut, S prime, is an xk, yk min cut. So all of the xk terminals are in here. This guy S is an isolating cut for T. So terminal T must actually be in this intersection. And all the remaining terminals in xk must be in this part, in S prime minus the intersection. Again, the intersection cannot contain anything more than T, because it's an isolating cut. It must contain exactly one terminal. Okay? And T cannot be here because T is in xk. So T must be sitting here, and the rest of the vertices in xk must be sitting in here. Okay? So now that we have made this observation, let's write the following inequality, again a very standard inequality that follows from submodularity. Okay, so this is saying that the size of the cut S plus S prime is at least the union of the two plus the intersection of the two. All right. So what is this intersection? So this is also a T isolating cut. Right? So this intersection also defines an isolating cut for T. What about the union? This union is also an xk, yk cut. Right? So if I take the union, the set of terminals in it is actually xk. So the fact that this is an xk, yk cut and S prime was the minimum xk, yk cut, that implies that f of S prime is no more than the size of this union. Okay? S prime was the minimum xk, yk cut, and this union is also an xk, yk cut. So that gives me this inequality. Based on this, I can now claim that f of S must be at least f of S intersection S prime. So if S was an isolating cut for T, S intersection S prime better be an isolating cut for T as well. And this cut, the S intersection S prime cut, will survive my contraction. So therefore, I will find this min cut. okay, because I will contract stuff on this side, on this yk side, and this cut will survive. Yes?
So yk is outside your window.
Yeah, yk lies here. Okay? So again, by this very standard inequality, just one application of the inequality, we can claim that all these contractions haven't destroyed my minimum isolating cuts. Okay, and therefore, what I return are correct minimum isolating cuts for all the terminals. Yes?
So since you're always crossing to the intersection, it's also fine to just start with any like containment minimal isolating minimum cut for each terminal?
So yes, so I mean if you define the minimum isolating cut as the containment minimal one, that will satisfy the disjointness property. Other questions? Okay, yeah. Why can't what? S be here inside this? That's possible, but that's a good case for me, because again I'm contracting the other side, xk, this side, because it contains t, I'm not contracting that. Okay. Other questions? All right. So hopefully you're convinced that the algorithm is correct. Why is the algorithm efficient? So here's the algorithm. I have gone over the algorithm a few times, so let me not go over it again. But really there are two places in the algorithm where I used ST-min cuts. Once I used it after I did that binary encoding, right? So there, how many calls did I make to ST-min cuts there? I made log t calls. And because I did a binary encoding for each bit location, I did an ST-min cut call. So that's good. I just have log t max flow calls there. The problem seems to be in the second step. So in the second step, what did I do? For every terminal, I contracted away some stuff, and then I ran ST-min cuts. I have t terminals, so it seems like I am back to where I started from. I'm still making size of t number of ST-min cut calls. And as Sapir pointed out, there's a trivial algorithm that makes the same number of ST-min cut calls. So what am I gaining in the process? Well, what I'm gaining is that I'm not making this second set of min cut calls on the original graph. I'm making it on a carefully constructed contracted graph. So if you look at the graph I'm looking at, so this is the kind of graph that I have. So I have a set Si that's uncontracted, and then everything outside in Zi is contracted. So what are the edges I'm encountering in this min cut call? I'm looking at these black edges that go between Si and Zi, and I'm looking at the orange edges that are inside Si. Now all these Si's are disjoint. So these orange edges only show up in one call for me, right? Every orange edge shows up exactly in one of the calls. The black edges show up in maybe two calls. Like if there's a black edge that goes from Si to Sj, it will show up in the ith iteration, it will show up in the jth iteration, but only two. So every edge shows up at most in two different calls. I'm running all these t min cuts on graphs whose edges add up to just twice the edges that I started with. So that means I can claim that although there are t min cut calls, the total time I take on them is about the same as constant number of min cut calls on my original graph. Okay? And once I make this observation, that gives us the isolating cuts lemma. So this lemma says that the isolating cuts, minimum isolating cuts problem can be solved using log t max flow calls. So that's an exponential improvement over what we naively started with, which was just iterating over all the terminals and running min cuts. Okay? So that's the first part of my talk. This is a complete proof of the minimum isolating cuts lemma. Any questions before I talk about applications? Yeah.
You say it is order log t max flow calls, but is that correct, or is it like time-wise that
Yeah, so I mean interpret that statement as meaning that it takes order log t times whatever time you take to run max flow on the original graph.
And this is like you can't say it as log t max flow call because now max flow can be solved in almost linear time.
No, even earlier we could like, so whatever, let's say m to the alpha was the running time of max flow. This says that your running time for isolating cuts is going to be m to the alpha times log. Yes.
Finally, since you don't know k, but it's enough to have a constant size approximation, you just do binary sets of k.
Yes, exactly. But I'm going to talk about that as well. Yeah. But you're right, exactly. Other questions? All right. So let's start off with the application that actually took us there, which is the global min cut. So now here's my global min cut algorithm, and this mirrors what Erwin just said. So how do I, the only question that I left unsaid is how do I find k, the number of vertices on the smaller side of the min cut? I really have no idea how to do that, but what I can do is I can just search over all possible values of k in doubling ranges. So I have an iteration that goes from 0 to log n. This is just trying to guess the value of k up to a factor of 2, and then I repeat log n times. This is just to make sure that I boost the probability of success. And within each of these within these two loops, all I'm doing is sampling vertices with probability 1 over 2 raised to I, and then running isolating cuts on this sample. Okay, and of all these cuts that we get, we report the minimum one at the end, and that's my global min cut algorithm. What's the running time? Everything else is linear time. The only thing that's non-trivial is the fact that I'm running max flows. Of course, thanks to Rasmus and his co-authors, max flow nowadays is also pretty close to linear time. So overall, this takes time that's almost linear. All right. However, this was already known. So even 25 years ago, it was known how to find global min cuts in a graph in time that's nearly linear. Okay, so what are we doing here? Why is this useful? Of course, this previous algorithm does not go through isolating cuts. It does something completely different. But in terms of a result, this is not improving what was already known. But there are a few advantages. The first one, and this is what actually originally made us start working on this problem, is that unlike the previous algorithm, this algorithm that I just described can be de-randomized. So for a very long time, for about 25-30 years, there was a huge gap between the running time of min cut if you allowed randomization, in fact if you allowed Monte Carlo algorithms, versus if you did not allow randomization or even restricted yourself to Las Vegas algorithms. Okay, and this gap was polynomial. So the first thing that this does is it improves the running time of deterministic min cuts. Okay. Now the running time that I've written here is a little worse than what I stated on the previous slide, just because the max flow gadget itself is slower. Okay. It's still just polylog times max flows. It's just that a deterministic max flow is slower than a randomized max flow. Maybe not, I don't know. Rasmus is staring at me. I think maybe they have a result. I'm not privy to it. So, good. But in fact, after we came up with this result, my co-author Jason Lee, he came up with an even faster algorithm for deterministic min cuts, and that actually takes time that's almost linear. Okay, it should be m to the 1 plus little of 1, not m to the little. Sorry. Okay. But here's what I want to focus on. Another important property, perhaps even more important in hindsight, although we didn't realize it immediately when we were working on it, is that this generalizes, this isolating cuts framework generalizes well beyond the global min-cut problem. In particular, it generalizes to something called Steiner min-cuts, and I will talk about it in detail in the next few slides. So let me skip that. All it uses is some properties of cut functions, two properties essentially, submodularity and symmetry, and therefore it can be abstracted, and you can show various improvements in the running time of optimizations of minimization of submodular or bisubmodular functions. So this is work of Chekuri and Quanrad, and for hypergraph min-cuts, which can be cast as a special case of the previous bullet. This was also in the Chekuri and Quanrad paper, also independently observed by Mukhopadhyay and Anankai. Okay, so it generalizes. Let's look at Steiner min-cuts and see what's going on there, because that will lead to further things. So what's the Steiner min-cut problem? So this is a generalization of ST min-cuts and global min-cuts. So ST min-cut says I give you two vertices, separate them. Global min-cut says I give you the entire set of vertices, separate them. Now you can see where I am going. Now I can give you any arbitrary subset of vertices and ask you to separate them in an optimal manner. And that's exactly Steiner min-cut. I give you a graph, I give you an arbitrary set of vertices, let me call that S. I want you to find the minimum cut that has at least one vertex of S on both sides of the cut. Okay. So that's Steiner min-cut. So in this particular example, if S is defined by these three vertices S, T1 and T2, then the Steiner min-cut is the degree cut for T1. Note that that's not the global min-cut. The global min-cut is the edge in the middle. Okay. So interestingly, for Steiner min-cut, even if you allowed randomization, the only algorithm that was known was this trivial algorithm that just fixes one of the vertices in S and then iterates over all the other vertices and runs ST min-cuts, okay, and reports the smallest one. So that would be the simplest algorithm. I fix one of the terminals, one of the vertices in S, iterate over the rest, find ST min-cuts for all of these pairs, and report the one that's smallest. And that was the best known algorithm till the isolating cuts framework came up. So how does isolating cuts solve this problem? Well, actually by completely trivially extending what I just gave you as the global min-cut algorithm. So here's my extension, and I have marked the parts that are new with purple, in purple. So all we are doing now is we are given this set S, and we are, instead of guessing the number of vertices on the smaller side of my min-cut, I am guessing the number of vertices from S on the smaller side of the Steiner min-cut. Okay, so I again run this iteration from 0 to log n. This is trying to guess this number. For a given value of I will repeat log n times. This is boosting the probability as earlier. And once I have a sample, now I am sampling only from the vertices in S. Once I have a sample, I run isolating cuts. Okay, and exactly the same proof works. So trivially now we can extend the global min-cut algorithm to a Steiner min-cut algorithm. Now this should be contrasted with the fact that if you take previous global min-cut algorithms, they're really specialized for the global min-cut problem. Even if almost all vertices are in S, a few vertices are left out, the algorithms don't work. Okay, so that flexibility is the flexibility of the isolating cuts framework is now showing up. And running time again is exactly the same. Running time is dominated by the isolating cut calls, and the isolating cut algorithm runs in time, that's polylog max flows. Any questions about this application? Okay. So let's organize the problems we have talked about a little bit. So we have really talked about three problems. The first one at the bottom on the left is ST min-cut. I haven't actually talked about how to solve that. That's Rasmus's job tomorrow. what I have said is how to use that to solve various other things. So that's the first problem, ST min cuts. Problem on the right is global min cuts. As I said, for a long time now, we know how to do this very efficiently in near linear time. Okay? But I did show you how you can use ST min cuts to solve global min cuts. And then I generalized these two to define Steiner min cuts. And in fact, this algorithm that utilizes ST max flows to solve global min cuts also solves Steiner min cuts with a trivial extension. So that's the state we are in. And all of these are solvable in polylog max flow calls. Let's generalize a little further. Let's ask for the following problem. So this is the single source min cuts problem. All of you know what the single source shortest paths is. So this is exactly the same, except it's min cuts rather than shortest paths. So I give you a graph. I give you a single vertex S. This is a fixed source that I gave you. I need you to report the minimum cut that separates S from every vertex. So for every vertex T, there's some ST min cut. I want you to report an ST min cut, okay, or at least the value of the ST min cut. Is the problem clear? How would you solve it naively? Well, I can just iterate over all the vertices T and run ST min cuts. Right? So I fix my vertex S, iterate over all the vertices T, all the n minus 1 vertices, run ST min cuts, and report these. That's the naive way of solving single source min cuts. Amazingly, till 2 years back, this was the only way for solving this problem. We didn't know of any other way of solving this problem. Okay? So that's my next problem, single source min cuts. Let's go even further. And now let's ask for all pairs min cuts. So now I don't even give you a source. I ask you for min cuts that separate every pair of, so for every pair of vertices, you have to report some min cut, or at least the value of the min cut. Okay, so connectivity for all pairs. Now interestingly, here the naive algorithm takes n squared max flows, right? So the naive algorithm for single source min cuts is just n max flows. Naive algorithm for single source for all pairs min cuts is n squared max flows, but for 60 years we know how to do better. So Gomery and Hu, in a classic algorithm in 1961, showed that in fact for even this more general problem, it's sufficient to just run n minus 1 max flows. You don't really need to run n squared different max flows. Okay? I'm not going to show you how, but this has been known for a long time. So the state is that the state is that the top of that picture is muddy. We know max flow algorithms that run using n max flow calls. The bottom of this picture now is clear. We know algorithms that run in polylog max flow calls. Okay? Now the first dent at this picture was a few years ago when several groups, Abud, Krautgammer, and Trabelsi initially, and then in a slightly more refined way, me with Jason Lee, and then me with Thachepol and Jason, we showed that the last two problems on top are also equivalent up to polylog factors. Okay? This is similar to saying that the ST min cut problem and Steiner min cut are equivalent up to polylog factors. So the bottom equivalence was shown through isolating cuts. I showed it at the beginning. Now we know that the problems on top are also equivalent. Okay, so if you can solve single source min cuts, you automatically solve all pairs min cuts. Okay, you just lose polylog factors. So this is our picture. Let's freeze the bottom of the picture. Okay, we know good algorithms there. We are pretty much done. Let's see what we can do at the top. And to start looking at these problems, let's first make the problem easier, make life easier for us, and ask, can we even get 1 plus epsilon approximations? This is an easier problem, but nothing better was known. The only algorithm that was known is the Gomery-Hu algorithm from 60 years ago, and the only algorithm for all pairs min cuts, only algorithm that was known for single source min cuts is the trivial algorithm that iterates over all vertices. okay, even if we allow approximations. How much time do I have? 10 more minutes? 20 minutes? Okay, half an hour, good. Okay, so that's what we have now. Any questions at this point? Is this picture, any questions about this picture and where we are? Okay. So the first question you might ask now is, now I have allowed myself approximations. So if I am allowing approximations, does that polylog equivalence on top still work, right? Or is it very specific to exact algorithms? And that's where these different references differ a little. Right? So the initial ones weren't explicitly tackling approximations, the later ones do. So with these better reductions, the ones that came later, we know that this reduction actually is robust to approximations. Okay, so if I get a 1 plus epsilon approximation for single source min cut, I automatically get a 1 plus epsilon approximation for all pairs min cuts. And this is not quite trivial. In fact, conceptually, this was one of the bottlenecks that prevented us from getting approximate algorithms for all pairs min cuts problems. For many years, this was a conceptual bottleneck. But now that we know how to do this, the question then arises, can I now solve the single source min cuts problem well if I allow you approximations? So let me give you a trivial sounding framework for this problem. And here's my framework. So I will iterate, so I denote my source S, this is given to me. Now I iterate over values of k in powers of 1 plus epsilon. And for each value of k, all I want you to do is report all the vertices whose min cut from S is value k or smaller. Okay, so I start with, let's say, k equals 1. I want everybody whose min cut from S has a weight of 1. Then I go to 1 plus epsilon, I want everybody whose weight is at most 1 plus epsilon, and so on. So if I am able to solve this, then I actually am able to solve the single source approximate min cuts problem. Because in every step, when I go from, let's say, 1 plus epsilon to the I to 1 plus epsilon to the I plus 1, the new vertices that join my pool, they are precisely the ones whose min cut value is between 1 plus epsilon to the I and 1 plus epsilon to the I plus 1. So these new vertices, I know their connectivity, their min cut value exactly up to an approximation of 1 plus epsilon. So if I'm able to solve that problem, just find, given this fixed vertex S, find me every vertex whose min cut is a value k or smaller, then I am able to automatically solve this approximate min cut problem, approximate single source min cut problem. Questions about this? So let me take that question and abstract it out into a new algorithmic problem. So we call this the cut threshold problem. So what is the cut threshold problem? I give you a graph, I give you a source vertex, I give you a threshold k. Find me all vertices whose connectivity to S is k or smaller, whose min cut separating it from S is of value k or smaller. I'm not asking for any of the values, I just need this set. Okay? So it's everything that's below the threshold, I want to separate them from everything that's above the threshold. Okay, so we want to solve this problem, and again, thankfully, isolating cuts comes to our rescue. How do we solve this? Okay, so that's the problem again. Now, a key property of single source min cuts is that these cuts are not arbitrarily organized. In fact, if I fix this vertex S and look at the single source min cut from S to every other vertex, then these cuts form a laminar family. Okay? So one way of representing this is through this kind of a tree. So I have this vertex S somewhere in this tree. I have all these edges. Every edge represents a cut. right. So, if I remove the edge, vertices split into two parts. And now for every vertex, I can simply find its minimum cut from S as the minimum value of any edge going from that vertex to S, the unique path that's going on the tree. Okay. So, all the ST min cuts for a given vertex S are organized in a laminar way. This is a property that's been known for 60 years, it's not new. So, now let us say somebody comes and says that, well, let us set k equals 2. I want you to report every vertex whose min cut from S is of value 2 or smaller. What is it that the person really wants? Well, what I need to report are these two yellow blobs, because all these vertices that I have shown in yellow here are separated from S by some edge that's of value 1 or 2, some value that's at most 2. The vertices on the left are not separated from S by an edge of value 2 or smaller. Okay. So, I really just need to report in my cut threshold algorithm, I need to report these two sets X and Y. Of course, I have no idea what this tree is, but if somebody gave you the tree, this is what you needed to report, just all the vertices in X and all the vertices in Y. Okay. So, how can I do this efficiently? Okay. Questions? Okay. So, let me denote by X and Y the roots of these subtrees, okay, the vertices that's closest to S. So, if I gave you, let us say X, this one vertex X, what would you do to identify this set capital X? Again, think of ST min cuts. What kind of an ST min cut would you run to identify capital X? Exactly, you would run an SX min cut. If I ran an SX min cut algorithm, what is it going to return? It's going to return X for me. Okay. And once it returns X, I not only identify X to be one of the vertices that has value less than k, but I identify everything in capital X. All of those are done. I have figured out a cut that separates those from S of value less than 2 or at most 2. So, if I had access to these vertices X and Y, then all I need is an ST min cut algorithm. I do not have access to these vertices. If I do not have access to vertices with special properties, there is only one thing I can do. I can try to sample and get these somehow. So, let us say I am able to sample a set of terminals T such that the following properties are true. First, S is in my sample. That is something I can force. I can just throw S into my sample all the time. So, S is in my sample. The second property, which is more crucial, is in the set capital X, only the vertex little x is in the sample, nothing else is in my sample. Okay. There is only one vertex from capital X in my sample T, and that specific vertex is little x. That seems a very low probability event for any sampling, but we will get to that. But suppose I had a sample of that kind, or similarly for Y, but let's forget about Y for a second. If I had a sample of vertices that contains little s and from capital X only contains little x, then I can still identify this set capital X. The sample may be more than 2 vertices, right. So, I can no longer run ST min cuts, but what can I run to identify capital X? I can run isolating cuts. If I run isolating cuts, that will isolate little x from the rest of the sampled vertices, and therefore, it will return capital X. So, now that is my algorithm. I want to sample vertices, we will see at what rate. I want to sample vertices such that it contains S and it contains only x, little x from capital X, and then I will run isolating cuts. If isolating cuts So if we can run isolating cuts, it reveals this cut x. Similarly, if in capital Y I only had little y in my sample, the isolating cut for little y will reveal capital Y. Okay. Now, what's the probability that I should be sampling at? So let's say I am sampling at rate about 1 over the size of x. Then this seems the right thing to do because I expect to see one vertex from x in my sample. I need little x to be the only vertex I see. So if I am sampling at about that rate, then with some probability in fact 1 over the size of x, I will precisely see little x as my sampled vertex from capital X. Right? I will see little x and nothing else with this probability. And then if I am able to do that, if my sample has that property, I am actually able to identify capital X number of different vertices, right? Not just little x, but everything under it. So that suggests that actually I am not in such a bad shape. My probability of success is relatively small, it is 1 over the size of capital X. But when I succeed, I really do well. I get all these vertices in capital X. Okay? And maybe if I repeat it log times, I will end up marking all the vertices that I needed to mark. Because in expectation, I am marking one vertex by this process. Right? I am marking with probability 1 over x, but I am marking all the vertices x in x. Now, of course, this is not completely kosher because this may not be uniform, some vertices may be left out. So, but this argument can be made formal. So, what's the overall algorithm then? So, here's my algorithm for solving cut threshold. Let's say U is a set that's V minus S. Okay? So, this is what I will be sampling from. Now, I repeat some polylog n times, that's again just to boost probabilities. I iterate from 0 to log n. This is because I don't know the size of x or the size of y. There's x, there's y, there can be a z. All these things might have different sizes. I don't know these values, so I have to guess. And then I sample every vertices from U at rate 1 over 2 to the I. I run isolating cuts on this sample after I have added S to the sample. Okay? Isolating cuts returns a bunch of cuts to me. If those cuts are smaller than k, I mark all the vertices that S is being separated from by those cuts. Mark those vertices, remove them from U, keep repeating this process. If a vertex is persistent, it decides to stay in U, I am not being able to mark it, it better be the case that it's actually connected with value more than k to S. So everything I end up marking at the end that's not in U anymore, these are the vertices I return for my cut threshold algorithm. Okay? So that's my overall cut threshold algorithm. Questions about the algorithm? Yes?
So at the end of this algorithm, you are recovering these numbers for each of the sort of non-S vertices, but are you necessarily recovering this laminar tree structure from the previous? Like, how do you distinguish between small x and small y being? How do you tell how to separate out these subtrees if they have comparable sizes?
Right. So the way I described it, you are just recovering which vertices are below k and which vertices are above k. The cut threshold problem per se does not ask you to return any numbers, it just asks you to return vertices that have connectivity less than k. So as far as the cut threshold problem is concerned, this algorithm is solving that problem. But there are ways that you can easily adapt this algorithm to actually also give you these cuts. Of course, it won't be able to give you cuts that are larger than k, but it will give you the cuts that are smaller than k. Other questions? Yes?
Does a similar algorithm work for symmetric submodular functions?
Does a similar algorithm work for symmetric submodular functions? So I'll need to think about that because so if you have just a generic symmetric submodular function, you have to think about what are the gadgets that you are using, right? Because you have to have some kind of an oracle model, and you have to figure out what are the different oracles that you are accessing. In principle, it should, but I'll have to think more offline to see what are the oracles that it might access. Yes?
But to solve the global min-cut problem using cut threshold, can you do a binary search on values of k?
So yes, but cut threshold, so you fix a vertex S, and then you binary search over values of k and see if anybody is separated from S. Yes, so that will work, but that's slightly circular in the sense that cut threshold is using isolating cuts, and even isolating cuts will solve the global min-cut problem. Other questions? Yes.
Just want to make sure I'm understanding the tree correctly.
Yes.
So basically, this is a tree where the min-cut between any two vertices is the lowest entry on that tree.
On the path, yes.
On the path.
Yeah, yeah. I mean, this is also what's called a Gomory-Wood tree.
Yeah, that's correct.
Other questions? Okay. All right, so that's our cut threshold algorithm. And as I said, once I have the cut threshold algorithm, let me go back to this thing. Sorry. So the cut threshold problem now solves the one step in this simple framework for 1 plus epsilon approximate single source min cuts that I didn't have. So now that I have a cut threshold algorithm, now I have a 1 plus epsilon approximate single source min cuts algorithm. And by the reduction that I described earlier, that implies that now I also have a 1 plus epsilon approximate all pairs min cuts algorithm. Okay, because as I said, this reduction that only loses polylog factors is robust to approximations. Yes.
Sorry, can you go back to the slide of the Gomory-Wood tree? Sorry, I'm just so the property of Gomory-Wood tree says that like the min cut between S, like if we see this edge labeled 2 between S and X,
Yes.
then we know that the capital X here on this side of the tree from that edge is a min cut between S and X.
Yes.
But how do we know that we will find that min cut? Like what if couldn't we also find a different min cut that has the same value?
Yes. So again, that's something that can be ensured. So in particular, you can find what are known as inclusion minimal min cuts. This is something I think Ellis mentioned. So if you look at all the min cuts between S and T and look at it from the perspective of T, then you can keep uncrossing until you get something that's the smallest, that's inclusion minimal. And by slightly perturbing your graph, you can ensure that the min cut that is returned always is the inclusion minimal one. Other questions? Okay, so in this picture now we have an approximate, a 1 plus epsilon approximate single source min cut algorithm and a 1 plus epsilon approximate all pairs min cuts algorithm. And both of these run in polylog max flow time. Of course, the last question that remains is this 1 plus epsilon approximation necessary? Can we get exact algorithms? This is something I will give you the answer. I will tell you almost nothing about how to get the answer because that's a talk in itself. But let me give you the answer first. So indeed you can. So you can obtain an algorithm for the all pairs min cuts problem or the single source min cuts problem, and thereby for the all pairs min cuts problem that runs in time that's about n squared, and this is the published result. You can actually get it in time that's almost linear with some more work. This is not something that only relies on isolating cuts, and that's one of the reasons that I didn't want to put the details of this algorithm in the talk. This does use isolating cuts, but sort of deep down in the algorithm in some particular situations. But I'll give you a very high level 2-minute overview of what this algorithm is doing. This is not going to do justice to the algorithm at all. But here's our 1 plus epsilon approximate algorithm that I just described. What was it doing? It was solving cut threshold, and for these exponentially increasing values of k with a base of 1 plus epsilon, it was finding all vertices with lambda st less or equal to k. Okay, lambda st being the connectivity or value of the st min cut. Now, as I said, in the ith step, what's going on is that you are finding every vertex that whose value of lambda st single source connectivity is between 1 plus epsilon I and 1 plus epsilon I minus 1. You are finding the vertices in between these two, and that is where the approximation is coming from. I am not being able to separate those vertices. So, at a very high level, what this new algorithm does is it is able to not only find this set of vertices, but it is actually able to pin down what the connectivity of those vertices is. And I want to emphasize that it is important that it is only doing so for vertices whose value of lambda st is very close to each other. Okay, so if you gave this new algorithm all the vertices, then without using this iterative layering, it won't be able to figure out the connectivity of all the vertices. Okay, but the new gadget, what it does is if you promise it that the vertices that you are asking it to find connectivity from S all have connectivity very close to each other within a factor of 1 plus epsilon, then or 1 minus epsilon, then the new algorithm says, okay, now I have this confidence, I can go ahead and find their connectivities for real. Okay. And you can set epsilon in this case to any small constant. You can fix epsilon to be 0.1 or something like that. Okay, so that's at a very high level, that's the thing that changes from the approximate to the exact algorithm. Of course, actually obtaining a solution to this involves isolating cuts, but also a lot of other techniques that I won't go into. Okay, so that brings me to the end of a discussion of the applications of isolating cuts. I haven't covered all the applications. There are other applications. For example, Roshu here has been working, my student Roshu has been working on using isolating cuts to find augmentation solutions. So how to augment a graph to meet connectivity targets. So that's a network design problem. So there are other applications beyond it. Some version of isolating cuts can be used for vertex connectivity. So there are applications like these that I haven't touched on, but I talked about a few of the main applications of isolating cuts over the last 2 or 3 years. Any questions about applications before I say a little bit about what happens next? Yeah.
Is it still open how to solve congruity trees in order n time instead of n squared? Is this even possible?
So we have a result current that can solve it in almost linear time, m to the 1 plus little of 1. Yes.
Does that laminar tree representation extend to the edge-weighted graphs?
Yes. Yeah, everything that I said here works for edge-weighted graphs. Yes. Other questions? Okay. Okay, so I want to leave you with sort of my musings about directed graphs. Everything that I said was about undirected graphs and really heavily uses undirectedness of the graph. Now, if you think about it, step back and think about it, what are the things that you really needed for any of these proofs to work? You need, or the isolating cuts framework itself to work, you needed the cut function to be both symmetric and submodular. Now, in directed graphs, you can get one but not both. So, if you define a directed cut to be what we normally think of it as, the set of edges going from one direction of the cut to the other, one side of the cut to the other, then that does have submodularity. It does not have symmetry, of course, it is a directed graph. Now, you can change your definition and you can think of the minimum cut being defined as the minimum of the two sides, right. So, when you say ST min cut, you can either say ST min cut is different from TS min cut, or you can say ST min cut and TS min cut are both the same, and it's really the smallest number of edges whose removal makes S and T non-strongly connected. Okay, both these definitions make sense. In the second definition, if we are forcing symmetry by just taking the minimum of the two sides for every cut, then we get, of course, symmetry, but we lose submodularity in the process. So really the question in directed graphs is, what can we do when we have only one of the two properties, when we don't have both? Okay. Now, even for the directed min cut problem, just the basic find the minimum cut of a directed graph, for a long time the running time of directed, and even now the running time of directed min cuts actually lagged that of undirected min cuts quite substantially. So in fact, this algorithm by Howe and Orlin from the early 90s was the best known algorithm for directed min cut till 2 or 3 years back, and its running time is m times n. And as I told you, for undirected graphs the running time already became near linear in the mid 90s. So there was a gap of n. Okay. So we had some result a few years back that does a little better. So instead of getting m times n, roughly speaking it gets basically it gets square root m max flows. So with the current max flow algorithms it gets about m to the 3 halves. Okay, so it gets a little better than m times n, but really not satisfactory at all. So, and also in terms of the algorithm itself, it just doesn't look like the right algorithm. It's balancing of various different things. So the question is the sort of philosophical question is there a suitable modification to the isolating cuts framework or the isolating cuts lemma that might be useful for directed graphs, and in particular can get us closer to the goal of getting near linear algorithms or almost linear algorithms for directed graphs. Now one thing to remember is that even for directed graphs, the max flow algorithms have an almost linear running time. So the current max flow techniques don't distinguish between directed and undirected graphs, the exact max flow ones. So if the isolating cuts type techniques might be useful because they do a reduction from global connectivity to these kinds of to max flow calls. So it seems like if one can interpret isolating cuts correctly on directed graphs, perhaps there's a way forward there. With that, I'll end the talk. Thank you. Isolating cuts I'm not, like I gave you the whole proof. This is exactly what it is. There are parts that are not so simple that I sort of kind of swept under the rug without actually saying so. So for example, de-randomizing the min cuts algorithm is more complicated than the min cuts algorithm that I presented here. Again, when you go to like single source min cuts, the algorithm I presented with cut threshold is exactly what it is. But the reduction from all pairs to single source, that's not so simple. That needs more technical work. So there are parts of this that need technical work, but what I did present is exactly what it is. There's nothing I'm hiding.
So in general, it's a bit of a vague question, but there are these older max min cut algorithms, this Nagamuchi, Warakia style algorithms that you reduce it to n-1 max flow, but those max flow subroutines are much easier than n-1 arbitrary max flow. They're like minimum spanning tree and things like that. Does isolating cut, can you say something about the max flow instances you have, for instance? Is there any chance that you can solve them using a simpler max flow algorithm instead of black box max flow?
That's a good question. So maybe I'll repeat the question. So the question basically is, isolating cut seems to be solving some specifically structured instances of max flow. Is there a chance that there might be simpler algorithms for these instances? I actually haven't thought about it. It's an interesting thought. I mean, off the top of my head, it's not clear because the second step is in fact very structured, but the first step maybe is not so structured. So, so that my first hunch would be that that would be the bottleneck. The first step might be fairly generic, but I think it's worth exploring.
But I just want to add to that a bit. Just when there are just two terminals, that's just a min cut, standard min cut problem. So I don't know if one can even simplify that and make it simpler than solving standard min cut thing.
Right. So, yeah. So, I guess like what Achapal is saying is like in the two terminal case you can't do anything more in the isolating cuts, but the way I interpreted Sapir's question is for global min cuts, it's not strictly necessary that you have to solve ST min cuts. So, there might be some way of like avoiding generic cases of ST min cuts completely.
And just as a motivation, there is currently a static max flow. Yes, we can solve it in almost linear time, but for instance, in parallel and those settings, we still don't have right algorithm. Is there a way that these things give you parallel?
So, in the exact world, no. In the approximate world, yes. So, Tachapal mentioned this idea of fair cuts. So, one of the motivations for us to look at fair cuts was that approximate max flow as a gadget in these isolating cuts and so on. So, if you use isolating cuts naively, then approximate min cuts is not a valid gadget for it because the approximation builds up. So, you have to use this more powerful thing called fair cuts, and fair cuts is actually solvable. Just like approximate min cuts are solvable in these other models, fair cuts are also solvable in these models. So, with approximations, yes. I'm sorry, I couldn't figure out all of the question.
Can you ever use isolating min cut to look at quickest transshipment where you don't just
quickest transshipment?
Yeah.
Okay. In like geometric settings or in general?
Like in the case where you don't necessarily care about having a max flow, but rather pushing a feasible flow through in a reasonable amount of time.
But one, like I guess, like at least for the standard transshipment problem, one special case of that is that you are pushing a max flow, right? I can ask you to send a shipment that's equal to the max flow.
So in that case, like, can you use isolating cut?
So, I mean, there might be multiple versions of transshipment. The versions that I am familiar with are basically flow problems. So, they are closer to ST min cuts. So, what I presented is taking ST min cuts as a gadget and solving various other problems, but transshipment really is ST min cuts itself.
Other questions?
Yeah.
What you have is for like two cuts. Like two cuts are polynomial. Do you think like when you're considering k cuts, it's hard, it's no longer polynomial. Like it's polynomial in fixed k. But like, can you see a version of this isolating cut lemma that will be helpful for like k cuts?
By k cuts, do you mean like I have k term, like k way cuts?
Yeah.
Or yeah, no, I mean these are NP hard problems, so yeah, I don't see the connection. Yeah.
Any other questions? Okay, if not, let's try that again.